So I want to do one more recurrence relation just to show you how to deal with things with numbers that aren't just powers of 2. All right, so let's define our recurrence like this. So t of n equals 5 t of n over 2, and t of 1 just equals 1, let's say, for simplicity. And so what we'll do is, the way to interpret this is basically somehow this algorithm is cutting the input in half. So it's every time it recurses, it feeds into its recursive calls half the size of the input as originally, but then it recurses 5 times per call. So this feels a little weird. It's probably not an array algorithm, but it may be something that deals with matrices or with numbers. And we'll see when we get to divide and conquer. We'll see plenty of examples of algorithms that do this kind of thing. All right, so here's the auxiliary step. I'm not going to belabor this because you've seen a whole bunch of these already. But I want to do this so that you can see a few nice techniques down below. All right, so if x equals n over 2, then I have t of n over 2 equals 5 t of n over 4. So I know I'm going to need to compute n over 4, so let me just do that. So t of n over 4 equals 5 times t of n over 8, right? So this is fine. This is not surprising, not at all unexpected. So my t of n equals 5 t of n over 2, or it equals 5 times t of n over 4. So let's say 5 times 5 times t of n over 4. Or it equals 5 times 5 times 5 times t of n over 8. Right? What's the pattern? Well, n over 2 here is n over 2, right? N over 4 is n over 2 divided by 2. N over 8 is n over 8, or is n over 2 divided by 2 divided by 2. So every time I divide by another 2, I multiply by another 5. So this is just 5 to the power of k times t of n over 2 to the power of k. Okay, so my anchoring step is just as simple as we've seen, all along here. So anchoring step gives me n over 2 to the k equals 1, or 2 to the k equals n, or k equals log base 2 of n. All right, so how do I deal with these? So now, I can get rid of my base case really easily here. I can get rid of my recurrence really easily, but I'll still have this kind of frustrating, mess with the 5. So I have 5 to the k. I'll just leave that as k for now and deal with it in a minute. Times t of 1, which I've defined as 1, right? So 5 to the k is the answer here. So k is log base 2 of n. So when you run into something like this, just start plugging stuff in and see what you find. So here, if I have 5 to the k, and then I substitute this expression in, I get 5 to the log base 2 of n. Okay. So now what do I do with this? Right? How is this a useful object? Well, it turns out that we can apply another log rule. And we can actually swap the locations of the n and the 5. So it turns out that this exactly equals n to the log base 2 of 5. Okay, so we went from it being n. Let's see. Just a moment. Sorry. Okay, so we went from it being 5 to this weird log of n to just being n to the power of this weird log of 5, okay? But this is just a polynomial complexity, right? So log base 2 of 5 is a number, right? So this is n to the power n to some number. In fact, it's approximately 2.32, right? So this is approximately equal to 2.32. So this is approximately n to the power of 2.32. So it's a little worse than quadratic time. So, we can say this is big theta of n to the 2.32. Plus or minus a little bit of error in there. So one thing that's worth thinking about is, why is it the case that we had this swap of the 5 and the n? So here's a little mathematical aside. Math aside. I want to prove that 5 to the log base 2 of n equals n to the log base 2 of 5. Okay, so why is this true? Well, I have two things here, and I can take the logarithm of both sides. Right? So I can just take the log base 2 of both sides here. So log base 2 of 5 to the log base 2 of n equals log base 2 of n to the log base 2 of 5. Right? So now once I have this, I can use the log rule that says log of something to a power is that power times log of something. Okay, so I can take these powers and multiply them in front. Right? So this is a fundamental log rule, and this is something you should memorize. This is key. So what does this give me? This gives me log base 2 of n times log base 2 of 5. And this equals what? This equals log base 2 of 5 times log base 2 of n. And sure enough, right? The thing on the left equals the thing on the right, right? So the equal sign checks out, and we're done. Okay, so this is one of these log rules that doesn't feel like it should be true and makes no sense why it should be true, but there it is. It's true, right? Once you actually go and verify this thing, you end up with these two statements being exactly equal. And so this is going to be handy as you go forward, especially into divide and conquer. But I believe also there may be a homework problem where this is a relevant thing to do.